Alright, Chapter 8, OSPF, Single Area. Alright, here's the bread and butter of the course. A lot of questions from the CCNA are based on this chapter alone. So of all the chapters, this is the one you need to focus on. Alright, let's begin. So again, remember in the early days we had RIP, and then Cisco came out with IGRP, and then the standards organization said, hey, we should have a standard one that works this well. So they made OSPF, and then Cisco made EIGRP, that kind of thing. So OSPF version 2 is really the one we use for IP version 4. And it was came out in 1990 or 1988, and then OSPF version 3 came out in 1998. I'm sorry, 1989. Sorry, that dyslexia kicks in. All right, so relatively new as far as networking goes, but in 2008, OSPF version 3 was updated with a lot more support for IP6. So at this point today, if you're going to do IP version 4, we're running OSPF version 2. And if you're running IPv6, you're running OSPF version 3. All right, so OSPF. OSPF is very efficient. It doesn't send updates all the time. It just sends small hello packets every 10 seconds. It only sends a change when a change occurs. It only sends the change to those people that need it, that kind of thing. So it converges fast. When a link goes down or a link comes up, the other routers communicate about it right away. And it happens very fast. It's also scalable. You can grow it to very large sizes. It's relatively secure. And obviously it's classless. We don't do class-full stuff anymore. Alright, so there are 3 databases inside OSPF. There's a neighbor table, a topology table, and a routing table. So the neighbor table obviously is pretty easy. It keeps track of all the directly attached Cisco equipment to the router. Alright, then it keeps a topology table. Now the topology table is like a map of the entire network, and all routers within an area have an identical link state database or topology table. And that way, when something happens, all routers have the information to make the change right away. All right, and then obviously it has a routing table with the routes it knows about. All right, OSPF has 5 packet types: hello, database descriptions, link state updates, link state requests, and then obviously the acknowledgments. Now, hello packets are sent every 10 seconds just to say, hey, that I'm still alive. So it's kind of like a keep alive mechanism. So hello packets establish adjacencies. So when one router receives a hello packet from another, then they both realize, hey, we're both on OSPF area 0. Let's be buddies. And then they send link state or the link state packets, which really is like a database description. The database description is like a summary of the routes that the router knows about. So he sends that to his neighbor, and his neighbor gets and says, hey, you know about 2 routes that I don't know about. So then that router sends a link state request asking for updates on those 2 networks. And then the first router says, oh, well, here's your updates, and sends those. And then acknowledgments are used, obviously, to acknowledge the other packets. So that's kind of how the packets work. The database description packet is like a summary of the route. It's like a summarized version of your routing table. So it shows you the routes that you know about and sends it to your neighbors. And then if they see a route that they don't know about, they can request more information, and then you send them an update to fill in that request. And then again, acknowledgments are to answer the replies. So those are the 5 packets. So when your routers first boot up, they catalog the directly connected networks. So here on R1, he knows about 10.1, 10.2, 10.3, and 10.4 because they're all locally connected. So he puts those in his routing table. Well, then he sends hello packets out saying, hey, I'm in OSPF area 0, and these are the 4 networks I know about. And then, well, let's go back to the beginning. So once he starts up and he knows that these are directly connected, then he sends hello packets out to find any neighbors. So R4 receives the hello packet and says, oh, hey, I'm in area 02. And then he sends that. So now R1 and R4 realize they're both in the same area. They both have some of the same timers. So then they form an adjacency. And once that adjacency is formed, then they become neighbors. They know they're sharing information. Then they start trading information about their routing tables. So in short, we send hello packets to form the adjacencies, to make those relationships. Once the relationships are formed, which Cisco calls adjacencies, then we start trading routing information. So once our relationship is formed, the routers all exchange LSA, link state advertisements, to each other. And the advertisements show, hey, these are my connected links, these are your connected links, things like that. So all routers are sharing this information. So these link state updates get flooded out the entire network. That's why whenever there's a power outage in your network and you don't have battery backup and everything boots up at the same time, for the first 5 to even 10 minutes, your network can be really slow and still have issues. Your routers are learning about the other routes that are in the network. Your switches are going through spanning tree process. You know, the DNS server's learning stuff. All the PCs are hammering, saying, hey, I need an IP address. Hey, I need some DNS information. Hey, I don't know where anything is. So there's a lot of traffic that generates when a network is freshly booted. So these LSAs go out, and the whole network is flooded with these over and over again. So R1 sends an LSA to R4, R4 sends an LSA to R2, R2 is like, oh, hey, he just told me information about the 1010 network, I didn't know about that. So then he adds that to his routing table, and he sends out another LSA. And then R2 sends him information about the 10.9 network. So then he makes another LSA. So these LSAs get flooded, blah, blah, blah. Eventually, all the databases of all the routers in the area converge. So they all have all the information. There's no new information. Once you quit getting LSAs, with new information, then the spanning or the shortest path first algorithm is executed. And at that point, costs are assigned to each link. So spanning tree assigns a cost to each link and then chooses the path with the lowest cost. So in order to go from R2, so let's say I'm up here on the 10.5 network, so my PC's up here, and he's going to go to R2, and then to R1, and then to R3, then he's going to go to a PC down here on this network here, this 10.6. So his total cost would be 2 plus 20, 22, plus 5, 27, plus 2, 29. So it would cost him 29 to get all the way to here. Now, that's how we look at it. Your router only looks at it from his point of view. So from his point of view, from R2, it's just 25 and 2, so it would be 27 to get here. But your total cost from your PC would be 29, because obviously he has a cost of 2. All right, and these costs are calculated for the entire area. So if there's, I guess, different buildings, things like that, you can change it up and you can have multiple areas. So like over here, Area 0 could be the headquarters network, and then Area 51 could be the data center, and then Area 1 over here could be something else. So we always start with Area 0. So Area 0 is like the backbone area. And then as we branch out, we can add areas. Remember, the advertisements and stuff only communicate to routers in their area. So all these updates from Area 0 would not go into Area 51, and Area 51's updates would not go into Area 0. And that way we can kind of administer the traffic and kind of filter it out from where it needs to go. And as part of that, when a link comes up or down, so the link state changes, the state's up, the state's down, that kind of thing. So when the state changes, those only impact the area, so it's not generating extra traffic into Area 1 and Area 0. All right, in the CCNP coursework, you get into multi-area OSPF. But at this point, I think they're in phase 2 of the new CCNA program, we only do single area OSPF. And then later on, when you get into scaling networks, we add multi-area OSPF. It used to be under the old program that CCNA only covered the single area stuff, but now you will be responsible for single and multi-area OSPF. But again, that's not a topic of phase 2 yet. All right, again, the OSPF packet types, there's the hello, the database description, link state request, link state update, and then the acknowledgement. Remember, hello packets form adjacencies between the neighbors, and they also work as a keep alive mechanism. If router 1 doesn't hear a hello from router 2 for several intervals, he's going to assume that link is down because he's not hearing anything. But if he does get hello packets, he knows that that link is up. So hello packets kind of work, as keep alives, but at first they work to discover neighbors and then decide which neighbors are part of your same group. And then once neighbors are in your group, we send database descriptions, which again really is like a summarized version of the routes that you know about. It just has minor information. Hey, I know about this route, I know about this route, I know about this route. And then if another router gets that and he sees one that he doesn't have, he'll send a request and says, oh, hey, I request more information on this route that you mentioned in your DBD. And then you send him back an update. Oh, hey, here's the information you requested. And again, acknowledgments just acknowledge that you received the other packets. So the hello type is very important, especially when your routers first start up. The hello packets go out and they have a little bit of information. They're like, hey, I'm in area 0, my hello time is this, my dead time is this. So they discover neighbor. So a hello packet hits your neighbor and your neighbor looks and says, oh, I match all that stuff. So certain things have to match for the adjacency to be formed. Obviously they need to be in the same area, their hello timers need to be the same, and their dead timers need to be the same. Now we'll get into all that in just a minute, but so realize it's not just because we're in area 0 that we form those adjacencies. There are 3 criteria. Our hello timers, our dead timers, and our areas have to be the same. If they're not, we will not form an adjacency. And they also have other information that's used to elect the designated router and the backup designated router. So the DR and the BDR, and we'll talk about those in just a second. Alright, so the hello packet looks like this. Again, you can see the area ID, so area 0. You see the hello interval, what's the space between hello packets, or I'm sorry, hello messages. And then the dead interval, how long till I mark a route till it's down. And then you see, hey, here's who I think the designated router is, who's the backup designated router, that kind of stuff. So all this information is in the hello packets, and it's used to form the adjacencies. If some of the stuff doesn't match, then we don't form an adjacency. All right, hello packets by default are sent every 10 seconds. And they're sent on a multicast address. So we don't broadcast these things. When you turn on OSPF, your router's listening on 224.0.0.5. So make sure you know that IP address for OSPF, 224.0.0.5. And it's FF02:5 in IP6. So every 10 seconds, hello packet. Hey, here's my hello, here's my hello, here's my hello, that kind of thing. Now, if you're on a non-broadcast multi-access network, such as Frame Relay, it knows that and it automatically changes to every 30 seconds. Obviously, these Frame Relay networks and things are on a much smaller bandwidth links, so you don't need it every 10 seconds. All right, the dead interval is the period that the router waits to receive hello before declaring the neighbors down. And Cisco's default is 4 times the hello. So basically, router 1 and router 2 are connected. They formed an adjacency. They're all set up. If router 2 doesn't send a hello packet 4 times, then router 1 then marks router 2 as down, and he tells everybody else, hey, this guy is down. So by default, hello packets every 10 seconds. The dead interval is every 40 seconds. So if I miss 4 hello packets, I will drop the or I will mark the line as down until I receive another hello message. All right, and it's kind of neat. You can see these different operational states of the links. So obviously the link starts as down, then it initiates, then it does a two-way, then it starts exchanging information, and then it exchanges databases, and then it loads the databases, then it goes to full. Now, if you do like show interface and you keep spamming it, you can actually see the state transition from like, initializing and then two-way and then exchange, and then eventually it'll say full. But once it reached the full state, then you've converged and you're operational. All right, so how does OSPF work? Now, if you're in the classroom, basically we grab a 3x5 card, everybody writes a 5-digit number on it really big, and then they sit it on their desk. And then they grab a piece of paper and they stand up and they walk around the room and they have to write down at least 6 other numbers from other people's desks. So basically what happens, the whole room stands up, there's a big cluster F as everybody's walking around and trying to grab information, so it looks miserable. And that's exactly what happens in OSPF. We form all these adjacencies, we're flooding information out. and it creates a lot of traffic. So what OSPF does is it elects one router to grab all the information, make the decisions, and then pass that out to all the other routers. And he becomes the designated router, so one router to rule them all. So the DR. Remember, the DR information is stored in the hello packet, so you can choose an OSPF priority. So by default, the router with the highest OSPF priority becomes the DR. Now the default is 1, so on your OSPF priority, if you don't change it, everybody's at 1. If you change it to 0, then that router will not be part of the election process. So basically he bows out of the race. Now, most of the time we don't set the priority. So then we go by the highest router ID. If the router ID is not set, we go by the highest IP address of a loopback interface. Excuse me. If that's not set, then we take the highest configured physical interface that is operational. Now, it's never a good idea to take the highest physical interface that's operational, because if something happens and that link goes down, then he changes the information and then there's a new election process that happens. So if your DR is elected the DR because of a physical interface, has a high IP address, and that interface goes down, then it causes a new election and somebody else may become elected. And then when your physical interface comes up, it doesn't cause a new election because the new DR is still operational. So an election only happens when the router starts up and there's not a DR. So once a DR is elected, he's the DR for life until that router goes down, until OSPF is shut off on that router, that kind of stuff. So that's why you have to be very careful about which router is elected the DR. So just make sure you understand there's an OSPF priority, and by default that is 1. So if everybody is on default, then it goes to the highest router ID, and the router ID is done with a command. If you have not put that command in, then it takes the highest IP address of the loopback interface. So again, you can see where these loopbacks kind of come in handy. A loopback interface never goes down. So if I want router 5 to always be the DR, I could just go there, give him a loopback IP address, 255.255.255.254 or something. Well, you get the idea. I can give him a high IP address, and then he would always be the DR. So make sure you understand this election process, because what happens is on the CCNA, they'll give you questions and they'll show you information. Hey, this router has a router priority of 1, this router has a router priority of 5. Which one will become the DR? Well, it's the highest OSPF priority. All right, so if you don't use router priority, then we do the highest router ID. And the router ID is put in with the router ID command. So nice and simple. So router OSPF 10, enter, and then router ID 1.1.1.1. So remember, it's the highest router ID. Then, if we don't set an ID, it takes the highest IP address of a loopback interface, and then after that, again, the highest IP address of a physical interface. All right, so again, to turn OSPF on, obviously router OSPF 10. So again, router OSPF 10. So now, this 10 here is a, oh crap, what do they call it? It's like a process ID number. It's only valid to the router. So this number does not have to match on the two routers. So you can put in router OSPF 10, I can put in router OSPF 20, and we would still form an adjacency if our other issues or our other things are correct. So just remember, router OSPF 10, this 10 number is a process ID, and its only importance is to the router itself, so it's only locally significant. So we can have different ones of that. And later on in phase 3, when we get into EIGRP, that totally changes. EIGRP uses this number, OSPF does not. So make sure you're good with that part. All right, so then again, you have to advertise your networks. So we use the network statement. So router OSPF 10, enter, and then network statements followed by an area ID. And then that's how we designate which area these networks are going to be in. And that way, if you've got a border router that's on the middle between area 0 and area 1, you can put one interface in area 0 and one interface in area 1. Now, don't forget these network statements. Here in the books and stuff, they typically show you an inverse subnet mask, so an opposite subnet mask. So 255.255.255.0 becomes 0.0.0.255. Now, on the exams and stuff, they still use that, but many of the operating systems nowadays, when you can actually type these in with the forward address, and everything still works. So make sure you're good with that, because sometimes in the lab you can get away with putting in 255.255.255.0, but if you do that on the exam, they'll mark it wrong. All right, another thing about the network advertising statements. This does not say advertise 172.16.1. What it says is, it says, hey, if any interfaces are operating on 172.16.1, then advertise the network of that interface. So let's say I had an interface that was working on 172.16.1 something, and it had a /25 subnet mask. It would still be advertised because it matches the first 24 bits. So that part gets confusing, especially with the network statements. Because a lot of times what people will do, and they'll get sloppy, I could just do a network statement, hey, network 172.16.0.0.0.255.255, I can only advertise the first 16 bits. I'm sorry, yeah, first 16 bits. And then that would match 16.1 and 16.3. So I could do one network statement to do that. So the network statement just says, hey, any interfaces that match this, advertise the network of the interface. So I know it gets confusing, so again, if you have questions about that, make sure you ask in class. Now, for best practices, you should be as specific as possible with your network statements, because the last thing you want to do is, you create all this stuff, and then a year later you add another interface that you want to be in another area of OSPF, not area 0, or you don't want it to be a part of it because it's a test network, and all of a sudden it's propagating throughout your network. All right, now passive interface. Remember, just like in RIP and all the other things, if you have a router that has an interface, let's say fast Ethernet 00, and it goes out to the LAN, then there's only PCs at the other end of that interface, there's no need for you to be sending out updates out that interface for OSPF when there's no routers to receive it. So you want to do a passive interface on that to, obviously, to stop those updates. So you go to, router OSPF 10, and then passive interface gigabit 00. Now, you can also do passive interface default, and that makes all the interfaces passive. And then you just go back and then you say, no passive interface, gigabit 00, no passive interface 5. So if your router, let's say, has a lot of interfaces, maybe it's a layer 3 switch, and you've got a lot of different LANs that go out there. Let's say you've got 10 LANs that it connects to, and then it has 3 serial interfaces. Well, it's easier to just do a passive interface default to shut down everything and then allow the 3 than it is to do passive interface on the 10, if that makes sense. So again, passive interface will stop sending updates out that interface. It doesn't stop it from being advertised to other routers, that network, as long as you did the correct network statement. It just says, hey, OSPF is not going to send OSPF updates out that interface because there's nothing on the other end to receive it that needs OSPF. All right, so now let's switch to cost. With OSPF, what they do is they take the cost, and it's based on the speed or the bandwidth of the links. So that's one of the advantages OSPF has over RIP. RIP just looks at bandwidth. RIP just looks at hop count, where OSPF takes bandwidth. So with OSPF, if you've got a fiber connection between 3 routers, and then you get a dial-up connection between 1 router to get to the same place, it'll always take the one with the less routers, where OSPF will take the one that will actually get there the fastest. So what it does is, it takes, 100 million times whatever the bandwidth is in bits per second, and it generates the cost. So a T1 would have a cost of 64. Cat3 would have a cost of 10. Fast Ethernet Cat5 would have a cost of 1. But the problem was when OSPF was first created, or they were developing it, 100 megabits was super fast. That was like the fastest, crazy, amazing cable you could get. Well, then later on they came out with gigabit, and then later on they came out with 10 gigabit. So it couldn't compensate for the differences in speed on it based on its formula. So because of this, by default, OSPF treats Cat5, Cat6, and 10 gigabit all as the same value. So later on I'll show you how to change that value. But that's what RIP does, OSPF does. It has a cost value associated with each link. So if you do show IP route and just have specifically which one, it'll tell you what the metric is. So that the metric is 65. So and we know 65 would be a serial link plus a fast Ethernet link. So if I just do show IP route, so remember I learned it from OSPF, this is the target network that I know about. OSPF has administrative distance of 110, and then the cost is 65. And then this is the next hop address, this is how long I've known about the route, and then this is my exit interface. Again, make sure at this point you can read the routing table. Where I learned the route from, the route that I know, or the network, the remote network that I know about that's out there, the administrative distance from the way I've learned the route, the metric used by whatever it is. So if it's OSPF, the metric is this. If it's RIP, it's going to be a hop count. If it's EIGRP, it's going to be some big long number that's about 10 characters long. And then via the next hop address, how long I've known about the route, and then my exit interface. All right, so back to the issue with the 10, going from 100 megabit to gigabit to 10 gigabit. If you've got those kind of links in your network, you want to use those links and have those preferred. Like I'd prefer to use the gigabit over the 100 megabit. So I want to use Cat6 over Cat5, but EIGRP sees them the same. So remember, go back another slide. EIGRP sees the cost as the same. So what you do is you have to change the reference cost with the auto cost reference bandwidth command. So if you're doing gigabit, it's auto cost reference bandwidth 1000 and auto cost reference bandwidth 10,000 on the 10 gig. And that will subdivide the cost even more, so then it can tell the difference between Cat5 and Cat6. All right, so when you do a show interface, it'll show you the actual bandwidth. And remember, that's all OSPF does. OSPF just takes the bandwidth of the link and it assigns a cost based on bandwidth. And then it takes the path with the lowest cost. Now, EIGRP uses some other stuff. There's delay, there's load, and then there's reliability, some things. But EIGRP only uses the bandwidth. And if you want to see the bandwidth of your link, just do a show interfaces. And then each interface, the bandwidth shows up. So remember, this is MTU size, this is the delay, reliability, load, that kind of thing. So, and just a little side note, reliability, the higher number the better. So if it's reliable, 255 out of 255, then it's very reliable. With load, you typically want the load to be less. So transmit load and receive load. So I typically want a low number for my load. All right, so you've done everything, but now you want to I guess you're trying to design your network. You want it to take a specific path throughout your network. So you can also change the bandwidth command so it changes the calculation method. If I go to interface serial 001 and I say, hey, bandwidth 64, it changes the bandwidth number, which then changes the cost calculation. Now here, I change it to 64, so now it says, bandwidth 64 kilobits. Back here, it says bandwidth, 1544. So this is probably a T1. But if I want to prefer the T1, I can change it with bandwidth 64. Now remember, bandwidth 64, the bandwidth command, does not change the actual bandwidth. It doesn't change the speed that anything is sent. All it changes is the numbers used in the calculation of the routes. So that's all it changes. It changes the cost, which then changes which route gets selected. So that way you can kind of mold or sculpt your data through the network, the path that you want to take. You can then actually take things a step further, and you can actually change the cost yourself to pick a certain path. So IP OSPF cost, and then put in that number. And that will physically change just the cost value. So if I change the bandwidth, I change the calculation methods that generates the cost, which is used to pick the routes. Or I can just go and say, hey, change the cost itself, and then I'm kind of okay. So the bandwidth one gets confusing because when we change that, a lot of people, one, when you change the bandwidth, then you got to kind of figure out what the cost would be based on that bandwidth. So sometimes it's just easier to change the cost. All right. So then, if you want to verify OSPF is working, you want to see your neighbors, show IP OSPF neighbors. Now here the state is full. Remember we talked about those other states, you know, initializing, two-way, exchange start, exchange, that kind of thing. Here, and I think I said show interface, but really if you do show IP OSPF neighbor, and then you keep hitting the up arrow, enter, as the neighbor relationship's formed, here's where the state will keep changing, and you can kind of keep seeing it as those two routers are forming their neighbor relationship. Now the whole thing happens in a couple of seconds, so basically you got to spam through that stuff. But remember, full means, hey, we have established a neighbor relationship. All right, some other verifying commands. Show IP protocol. Show IP protocols is pretty important because it'll show you like what dynamic routing protocols you're using on the router. It also shows you what the router ID is set to, and then it shows you what network statements you have put in. So at this point, these are the 3 network statements you put into your router. All right, there's also show IP OSPF. Which again only gives you information on OSPF. Now if your router is running OSPF and EIGRP, show IP protocols will show you that information for both protocols that you're running. But if you know your router is only running OSPF, you can just do show IP OSPF. And again, you get the router ID and a whole bunch of other information. And you can see obviously this thing has obviously room to scroll down and show you even more. Okay. And then you can verify your interfaces with show IP OSPF interface brief, and this will show you the interfaces participating in OSPF, which ones have been advertised as OSPF. So show IP OSPF interface brief. All right, so that's about it for version 2. And really, with version 3, it's the exact same thing. Now, if you're running both of them on a router, obviously it would have separate, remember, IP version 4 and IP version 6 are kept separately on the router. It's show IP route and then show IPv6 route. Show IP interface brief, show IPv6 interface brief. So there's always 2 of everything if you have IP4 and IP6 running. So again, they're very similar. They're both link state protocols. They both use shortest path first. They both calculate based on the cost. They both use areas, and area 0 is the same. They both have the same packet types. So really everything's the same except for the IP addresses that are used. So again, IP6 just uses IP6 addresses. The commands all have IPv6 in there, so show IPv6 route, that kind of thing. Now remember, you have to turn it on. You know, IPv4 routing is enabled by default, but IPv6 is not. So when you do IPv6, the very first thing you have to do is it's IPv6 space unicast routing to turn it on. Now OSPF version 2 has very weak authentication, where IP version 6 obviously has much stronger authentication. All right, now here's where it gets weird. With IP version 6, each interface that you assign an IP address also gets a link local address or a private address that's only read on that LAN or that segment. So it's possible for a router to have 3 interfaces and have, I guess, 2 of their link locals to be identical. So as far as IP6 multicast addresses go, remember FF02:5 is the address that all OSPF routers listen to for updates and hello messages, and that's their multicast address for messaging. And then the BDR and the DR, remember the designated router and the backup designated router, they listen on 6. So make sure you have those 2 in your notes, especially for the CCNA. All right, so here's kind of a shot with OSPF version 6. So remember, first we have to turn on unicast routing, so IPv6 unicast routing, and then it's enabled. Now with OSPF version 3, it's a little bit different. Remember, we used to turn on OSPF at global, and then we also use the network statements on those. So, you know, like router OSPF 10, enter, network, 172.16.17, blah, blah, 1 dot area 0. We don't do that anymore. Now in OSPF version 3, we go to the interfaces specifically, and then we just do IPv6 address. I'm sorry, this is just the addresses. All right, sorry, got ahead of myself. That's not what this slide is showing. This slide is just showing how to interface, or how to IP address your interfaces. So we turn on IP version 6. We go to the interfaces, we give them a description, we assign the IP address. And instead of IP address, it's IPv6 space address space, we put on the IPv6 address. So that's all this is showing, how to assign IP addresses with IP6 to your interfaces. All right, so for OSPF version 3, remember the very first thing you have to do is make sure that IP6 is turned on your router. Then you can use the router ID command to pick which router you want to be the DR, the designated router, and the backup designated router. Remember, when the designated router dies, the backup designated router becomes the new designated router, and then a new election is for the backup designated router. All right. So again, we can do show IPv6 interface brief, and remember, anytime you assign an IP address, you also get a link local address. So all your interfaces will theoretically have 2 IP addresses if you've assigned an IPv6 address. So don't let that freak you out. Remember, the FE80 is a link local address. It's only specific to that link. So you can see that over and over again. So actually, right here, FEA DA0, so DA0, so all these interfaces have the same IP address, but it's the same because they're on 3 different links. So don't let that throw you off. All right, so again, you can physically assign specific link local addresses if you don't want to use the MAC address. So in this case, they're using FE80 and they're just assigning the links as the host address 1, or you can just let it go by default, and it'll grab, remember, the MAC address, and it adds FE in the middle of it. All right, same router ID command. So router ID followed by the highest loopback address, followed by the highest physical interface, and then the other commands. So we go into, whoop, sorry, I got excited. So, router or IPv6 router OSPF 10. So that turns on version 3 for you. Excuse me. And then we're setting the router ID, so same router ID command. Then we have Cat6 links, so we're doing an auto cost reference bandwidth 1000. And then we end. Then you can do show IP protocols, and you kind of see the information. But where it gets different here is here. Instead of using the network command, and this is where this is what I thought they were advertising in another slide. So in OSPF version 3, we don't use the network command anymore. We physically go to the interface and we put those interfaces in an area. So I go to interface gigabit 0, enter IPv6 OSPF 10 area 0. So the process ID area 0. And go to all the interfaces, make sure they're all part of the same process ID, because remember, process ID is locally significant to the router, so all the router interfaces have to be on the same process ID, and then put them all in the same area. And then boom, we're all in area 0 and we're all configured. So we do not use network statements in OSPF version 3. We physically just go to the interfaces themselves and we assign the interface to an area. And it's much more efficient, and I guess there's less chance of an issue. In OSPF version 2, and all the other routing protocols, we create network statements. But it's very easy for us to get lazy and make very broad network statements that grab networks that we did not want to advertise for some reason. Whereas with OSPF version 3, we're going to the interface itself, and then we're saying, hey, whatever network is on this interface, be part of area 0. And that way there's no chance of us accidentally allowing a network to be advertised if we didn't want it to. So I hope that kind of alleviates that or explains that a little bit better. All right, so then to verify your stuff, show IPv6 OSPF neighbor. Again, you want to look at the state to make sure it's full. Show IPv6 protocols, show you your router ID, what networks you're advertising, or what interfaces are participating in those networks or advertised. Show IPv6 OSPF interface brief. We'll show you what interfaces you've got configured. and then show IPv6 route space OSPF will show you what IPv6 routes you've learned via OSPF. And remember, with IP version 6, you'll see an IP address that you assigned, and then you'll also see a link local address. So it's not odd to see two addresses for IP version 6 on an interface. Woo! Alright, so to sum it up, OSPF version 2 is IP4, OSPF version 3 is version 6. It is a classless routing protocol that works very well. It converges fast, saves bandwidth. You turn it on with the router OSPF command, so router OSPF 10 or IPv6 router OSPF 10, depending on which version you're using. If you're using version 4, we use the network statements. If you're using version 6, we assign it specifically to the interfaces themselves, and that way all the confusing information about the network statements is gone. Alright, by default, hello packets are sent every 10 seconds. On a regular network, and then on a non-broadcast multi-access like frame relay, X25 ATM, so WAN technologies, it's every 30 seconds. And then the dead interval is 4 times the hello. Remember, in order for a relationship or an adjacency to be established between two routers, they need to be in the same OSPF area, they need to have the same hello timer, and they need to have the same dead timer. If my dead time is 50 and your dead time is 40, we will not form a relationship. Alright, and then again, you can do show IP OSPF neighbors to see who your neighbors are. Don't forget that OSPF elects a designated router, and then all the advertisements are sent to that designated router. And then that designated router builds a whole map of the entire area, and then he sends them out to all the other routers. So it's like if we didn't have a DR, everybody got up and just walked around and grabbed information from everybody else, so there'd be all this confusion on the network. Then when everybody sat down, you could not guarantee that everybody had a list of the exact same information. But if you elected one person in the classroom to stand up, gather all the information, and then copy that on 12 pieces of paper and hand it out to the other 12 students, then you could guarantee that all the information that all 12 students had was the same, and there would be a whole lot less traffic on the floor as that one person walked around gathering information. So that's what OSPF does. It elects a designated router. Everybody sends their stuff to the DR. The DR processes everything from his point of view and then passes it all back out to everybody else, so everybody else has the exact same thing. So in OSPF, you're either a designated router, you're a backup designated router, or you are a DR other, meaning you are not a DR. So when you see druther, it means you are not the DR or the BDR. So only one DR, only one BDR, then everybody else is a DR other. So they're not the DR. So if you see druther in there, it means you're not the DR. Alright, that wraps up this thing. Again, very informational overload topic. So a lot of information. If you don't understand something, make sure you bring it up at the beginning of class when you guys come in for your lab. Alright, let's see what's in Angel for this. Alright, all kinds of stuff in Angel. There's an OSPF cheat sheet here that has information about OSPF, the states, information about the BDR, that kind of thing. So it gets kind of in depth. Alright, then there's the commands. And I don't know, I should have kind of ripped off these first couple slides to kind of walk through some other stuff. Alright, there's an example of using OSPF 3. Wait for it. Oh! Where they show you all the different commands that they use, to enable the routers. And there is a video of configuring routers with OSPF version 3. So your assignments this week, again, you've got a quiz that you've got the whole week to do. Remember, this is due Sunday. You have assessment 8. And then at home, you're going to do configuring OSPF using IPv4. And then when you come into the lab, we're going to configure OSPF with version 6. So OSPF version 4 is your practice lab at home. Make sure you're doing those so that you get the information. You don't want to be coming in and wasting your time and not being able to get your lab done in class for IP version 6 because you didn't do IP version 4 at home and now you have no idea what commands to type in. So, any questions? Make sure you bring them to class. Again, this is a huge topic. Lots of questions on the CCNA. Remember, out in the real world, for every company, most of them are either using EIGRP or OSPF. If you use EIGRP, you tie yourself into only buying Cisco stuff, which for most people is not a problem. But for some that is. So I would almost say that the majority of networks that I've played with are OSPF because it's so popular and it doesn't lock people in. You know, you can use other vendors' routers and you're still good. All right, so that's it. We'll see you in class, guys. And remember, bring any questions to class. All right, have a good one.